On the morning of 4th February 1971, the assembly halls in Derby fell quiet. Rolls-Royce, the ultimate symbol of British engineering prestige, had collapsed into receivership. The company that built the Merlin to save Britain in wartime was now bankrupt, shattered by the financial weight of a single civil jet engine program. The RB211, tied to a punishing fixed-price contract to power the Lockheed L-1011 TriStar, development costs had spiraled completely out of control. Overnight, the livelihoods of thousands of factory workers and engineers hung in the balance, forcing an unprecedented emergency nationalisation by the state. It was a devastating paradox. On the test stands, the massive high-bypass turbofan was a mechanical masterpiece. Its three-shaft architecture promised to redefine global aviation. Yet that exact brilliance, relying on experimental materials and unforgiving deadlines, was bleeding its creator to death. But the real story of the RB211 is not only the story of a boardroom collapse, it is the story of how an engine that destroyed a British empire also became the only thing that could save it. Every week, we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in Derby in 1968. In the middle of the 1960s, the global aviation market was shifting with a violence that British engineering had not anticipated. The era of the early narrow-body jet airliners, machines that had made air travel normal, was closing. Airlines were demanding a new kind of aircraft. They wanted wide-body jets capable of carrying hundreds of passengers in a single cabin, requiring a massive leap in thrust that existing engines simply could not provide. To power these new giants, the world needed the high-bypass turbofan. A jet engine, a turbine engine that produces thrust by accelerating air and exhaust gases, was no longer enough. The new turbofan had to move much of its air through a large fan at the front, bypassing the core altogether. This drastically improved efficiency and thrust while reducing noise, a crucial factor as airports began facing noise restrictions. In America, Pratt & Whitney and General Electric were already building these immense power plants. In Britain, there was only Rolls-Royce. For the aero engine division in Derby, the stakes were existential. If Rolls-Royce did not build a high-bypass turbofan, they would be locked out of the new wide-body market. If they were locked out of the wide-body market, they would cease to be a major global player, relegated to supplying niche aircraft and legacy fleets. The British government, desperate to maintain its aerospace prestige, poured subsidies into Derby, demanding that the company secure a major contract to prove Britain still belonged at the top table of aviation. The opportunity arrived in the form of the Lockheed L-1011 TriStar, a new wide-body airliner being developed in California. Lockheed needed an engine, and Rolls-Royce, driven by a mixture of engineering arrogance and commercial desperation, determined they would win the contract at any cost. In 1968, they did. Rolls-Royce secured the exclusive deal to power the TriStar, beating their American rivals. It was heralded as a triumph of British industry, a moment of national celebration. But the victory was built on a foundation of terrifying risk. To win the contract, Rolls-Royce had promised an engine that did not yet exist. They promised it would be lighter, quieter, and more fuel-efficient than anything the Americans were building. More dangerously, they had signed a fixed-price contract, meaning they would absorb any development overruns themselves. And most dangerously of all, they had committed to a timeline that left almost no margin for error. The signature was on the paper, the factory floors in Derby prepared for the future. But the British engineers still had to invent the technology to make the promises real. In 1968, the ink on the fixed-price contract with Lockheed was barely dry. But the reality of what Rolls-Royce had promised was already settling over the factory floors in Derby. The British engineering team had committed to delivering a power plant that would outclass the best efforts of the American giants, Pratt & Whitney and General Electric. The target was the Lockheed L-1011 TriStar, a wide-body airliner that required an engine capable of producing over 40,000 pounds of thrust. This was a colossal figure, more than double the power of the earlier Rolls-Royce Conway engines that had introduced Britain to the turbofan age. To achieve this leap in power, The new engine could not simply be a scaled-up version of an older design. It had to be a high-bypass turbofan. A turbofan, a jet engine that moves much of its air through a large fan at the front, bypassing the combustion core altogether, was the only way to generate massive thrust while reducing fuel consumption and noise. The vast volume of bypassed air acts as a cushion, wrapping around the hot, screaming exhaust gases from the core, silencing the roar that had defined the first generation of jets. But spinning a fan nearly 3 meters in diameter created a profound mechanical challenge. In America, Pratt & Whitney was developing the JT9D, and General Electric was building the CF6 using conventional two-shaft layouts. A shaft is the central spinning axis that connects the turbine sections at the rear to the compressor sections at the front. In a two-shaft engine, one shaft spins inside the other, allowing the high-pressure core and the low-pressure fan to rotate at different speeds. It was a proven, reliable method. But Rolls-Royce engineers, drawing on decades of aviation pedigree, decided that a two-shaft layout was too long and too flexible for an engine of this immense scale. They chose a path of radical, brilliant complexity. They would build the RB211 around a three-shaft architecture. The three-shaft architecture, a design where three concentric shafts spin independently inside one another, was a mechanical masterpiece. In the machine shops of the Midlands, this meant an entirely new level of precision. Instead of two spinning axes, there were three. The innermost shaft would drive the massive front fan, the middle shaft would drive the intermediate pressure compressor, the outer hollow shaft would drive the high-pressure compressor. For the machinists and fitters at Derby, this design was unforgiving. It required 3 sets of bearings, complex lubrication systems, and perfectly machined splines. Yet the advantages were staggering. Because the engine was divided into 3 distinct thermodynamic zones, each section could spin at its own perfect aerodynamic speed. The compressor stages did not have to compromise. This allowed the engine to be significantly shorter, more rigid, and vastly more fuel efficient than its two-shaft American rivals. A shorter engine flexed less under the extreme aerodynamic loads of flight, meaning the rotating blades could sit closer to the outer casings without scraping them. Tighter clearances meant less air escaped, which meant greater efficiency. This was the breakthrough that had won the Lockheed contract. Airlines like Eastern Airlines, Trans World Airlines, and later British Airways looked at the fuel economy projections and saw an engine that would revolutionize their fleet economics. But the three-shaft architecture introduced a secondary crisis. Weight. The massive fan at the front of the RB211 required enormous blades. If these blades were forged from solid titanium, the industry standard material, the sheer rotating mass would be catastrophic. The fan disc holding the blades would have to be thicker, the bearings would have to be heavier, and the containment ring designed to catch a broken blade would have to be built like a bank vault. The total weight of the engine would obliterate Lockheed's strict limits, and under the fixed-price contract, Rolls-Royce would face immediate financial penalties. To solve the weight problem, the British engineers turned to an experimental miracle material, carbon fiber. Rolls-Royce had developed a proprietary carbon fiber composite they called Hyfil. Carbon fiber, a material made of microscopic, immensely strong crystalline filaments of carbon embedded in a resin matrix, was incredibly stiff and phenomenally light. It promised a fan blade that was half the weight of traditional titanium. In a British workshop, instead of forging hot metal, technicians would lay up sheets of black carbon fiber by hand, bonding them into the precise aerodynamic twist required by the fan. In the early test cells at Derby, the Hyfil blades seemed like an absolute revelation. When the prototype fans spun up, they sliced the air with a deep, resonant hum that mechanics had never heard before. The weight savings rippled backward through the entire engine. The fan disc was lighter. The containment casing was thinner. The RB211 was hitting its theoretical weight targets perfectly. The aerospace press and government ministers marveled at the ambition. Rolls-Royce was not just building an engine. They were attempting to leapfrog the American aerospace establishment with a shorter, stiffer, three-shaft power plant spinning revolutionary black plastic blades. It was a staggering display of British mechanical pride. The foundries poured the complex casings. The machine lines cut the intricate shafts. The vast test stands at Derby were reinforced and wired with analog telemetry to handle thrust forces that would have ripped earlier engines from their mounts. Everything was aligning. The mathematics worked, the architecture was brilliant, and the test cells waited for an engine that was about to meet the violent reality of the physical world. By 1969, the development of the RB211 had consumed the town of Derby. This was no longer just an engineering program, it was an industrial crusade. To build a high-bypass turbofan of this unprecedented scale, Rolls-Royce had to transform its entire manufacturing footprint. The engine was so immense, nearly 3 meters across the fan face, that standard aviation assembly techniques were entirely inadequate. In the assembly halls, the engines had to be built vertically, stacked like industrial monoliths over deep pits dug into the factory floor. If they attempted horizontal assembly, the sheer weight of the heavy casings would cause them to sag and distort before they were even bolted together. The precision required by the three-shaft architecture meant that every bearing, every spline, and every compressor blade had to be machined to tolerances that left absolutely zero margin for error. The sheer volume of human effort was staggering. Thousands of draftsmen, metallurgists, machinists, and fitters were drafted onto the RB211 project. The foundries in the Midlands worked day and night pouring the complex aluminum and steel casings, while the machine shops carved the intricate titanium discs for the hot sections. Test cells that had once comfortably housed early Conway and Spey engines had to be drastically rebuilt, reinforced with thousands of tons of concrete and steel just to contain the violent thrust of the new era. The supply chain stretched across Britain. Specialist subcontractors from Coventry to Sheffield were drawn into the orbit of the RB211, feeding high-grade materials, fasteners, and auxiliary components into the Derby lines. The engine was driving a whole ecosystem of British manufacturing, pushing the metallurgical limits of what could be reliably mass-produced. Inside the high-pressure core of the engine, temperatures were designed to exceed the melting point of the turbine blades themselves. To prevent them from disintegrating, the blades had to be intricately cast with microscopic internal cooling channels, bleeding cooler air from the compressors to create a protective boundary layer of air over the spinning metal. It was a thermodynamic high-wire act. The British government, watching from London, treated the Derby factory floor as a strategic national asset. The state was pouring millions of pounds of launch aid into the project because the RB211 was the only British response to the American wide-body dominance. Lockheed engineers frequently traveled from California to the Midlands, walking the production lines, inspecting the black Hyfil carbon fiber blades being laid up by hand, and waiting for the power plant that would lift their TriStar into the sky. In a Britain where a jet engine decided whether a national industry survived the transition to the wide-body age, whether thousands of Midlands machinists kept their livelihoods, and whether the country remained an independent aerospace power, the RB211 was not an abstraction. It was metal, fuel, labor, heat, sound, repair, extreme financial risk, and a terrifying amount of trust. When the first prototypes were finally wheeled out to the test stands, the sound they made was a revelation. It was not the high-pitched tearing scream of the early jets. Because the vast majority of the air bypassed the hot core, the exhaust was wrapped in a slower, cooler cushion of air. The result was a deep, earth-shaking rumble, a low-frequency bass that vibrated through the chest cavities of the engineers standing in the observation bunkers. As the throttles were pushed forward, the telemetry dials spun. The three concentric shafts spooled up independently, finding their perfect aerodynamic balance. The massive black fan bit into the air, pulling tons of atmosphere through the inlet every second. The thrust figures climbed, 20,000, 30,000, and finally approaching the monumental 40,000-pound target. The mathematics had been proven in steel, titanium, and carbon fiber. The three-shaft architecture was working. It was a moment of supreme, intoxicating confidence for British engineering. The engine was producing the power they had promised the world. But scale at this level is a brutal master, and a turbine roaring in a heavily instrumented test cell had not yet faced the chaotic reality of the sky. To understand the sheer industrial momentum of the RB211 program by 1970, one had to stand near the Sinfin test site in Derby. A test cell, a heavily reinforced concrete bunker designed to hold a jet engine running at maximum power while sensors monitor every vibration, temperature, and pressure change, was no longer just a laboratory. It was the beating heart of the Midlands. When the three-shaft engine spooled up to its maximum rating, it consumed tons of aviation fuel per hour, accelerating a column of air so massive that the low-frequency rumble could be felt in the chest cavities of workers miles away. This single engine family was supporting an entire British industrial ecosystem. Rolls-Royce employed over 80,000 people globally, but the aero engine division in Derby was the nerve center. The project pulled in suppliers from across the country. Lucas Aerospace was tasked with developing the complex fuel systems required to feed the high-pressure core. Smiths Industries provided the intricate instrumentation. Forges in Sheffield delivered the raw titanium billets. An entire generation of British engineering apprentices was trained on the uncompromising tolerances of the RB211's concentric shafts. Across the Atlantic in Palmdale, California, Lockheed was assembling the massive airframes of the L-1011 TriStar. The aircraft was a wide-body masterpiece, designed to carry up to 400 passengers in near-silent comfort, but it was entirely dependent on the British power units. Lockheed had designed the TriStar exclusively around the RB211. There was no alternative engine option. If Derby failed, Lockheed failed. For a brief, intoxicating period, the gamble seemed to have paid off brilliantly. The prototype engines, fitted with the revolutionary black Hyfil carbon fiber fan blades, were hitting their aerodynamic targets. Airline executives from Eastern Airlines, Transworld Airlines, and Air Canada reviewed the telemetry data and saw a power plant that would fundamentally change the economics of mass air travel. The RB211 was shorter, more rigid, and significantly quieter than its American two-shaft rivals, the Pratt & Whitney JT9D and the General Electric CF6. At the Farnborough Air Show, the British aerospace press declared that Rolls-Royce had not only caught up to the Americans in the wide-body era, they had mathematically surpassed them. This was the zenith of post-war British mechanical optimism. The assembly halls at Derby were running day and night. The foundries glowed with poured metal. The state, having provided millions in launch aid, viewed the engine as a symbol of national capability. The RB211 was physical proof that Britain could still build the heaviest, most complex, and most valuable industrial machines on Earth. The mathematics worked. The architecture was flawless. The three independent shafts spun in perfect thermodynamic harmony. The British government, the Lockheed executives, and the Derby workforce believed they had definitively secured the future. But a high-bypass turbofan singing on a static test stand in the Midlands had not yet faced the violent, unpredictable reality of the sky. The first crack in the RB211 program was not financial, it was physical, and it happened in a fraction of a second inside a testing bunker at Derby. A high-bypass turbofan ingests tons of air per minute, which means it will inevitably ingest anything occupying that airspace, including large birds. To achieve aviation certification, an aero engine must prove it can suffer a severe bird strike at takeoff thrust, safely contain the damage, and allow the aircraft to return to the ground. In a specialized test cell, British engineers simulated this violent reality by firing thawed bird carcasses from a pneumatic cannon directly into the spinning black fan of the RB211. What happened next shattered the optimism of the entire project. The revolutionary Hyfil carbon fiber blades were incredibly stiff and phenomenally light, but they possessed a fatal metallurgical weakness. They lacked the ductile strength of forged metal. When the heavy impact struck the composite material at high speed, the Hyfil blades did not merely dent or bend, they shattered. The sheer kinetic energy delaminated the carbon layers, sending jagged, catastrophic shrapnel backwards into the delicate high-pressure core. The engine tore itself apart on the stand. Engineers frantically attempted to solve the problem by reinforcing the leading edges of the black blades with steel shields, but the composite resin simply could not absorb the blunt force trauma of a major strike. The physics were absolute. Rolls-Royce was forced to abandon the Hyfil dream. They had to return to conventional, solid titanium fan blades. This single engineering retreat triggered a catastrophic chain reaction that would tear the company apart. The crisis was driven by the brutal reality of Force One: iron, aluminium, fuel, and manufacturing costs. Titanium is a magnificent aerospace material, but it is vastly heavier than carbon fiber. By switching the enormous front fan to solid titanium blades, the rotating mass at the front of the engine immediately doubled. Because the fan was now twice as heavy, the intricate fan disc that held the blades had to be redesigned and thickened to handle the massive new centrifugal forces. Because the fan and disc were heavier, the front bearing assemblies had to be uprated. And because a broken titanium blade is essentially a heavy, high-velocity projectile, the outer containment casing, designed to stop a broken blade from slicing through the aircraft fuselage, had to be massively reinforced with layers of heavy steel and Kevlar. Overnight, the RB211 became severely overweight. This weight penalty destroyed the delicate thermodynamic balance of the three-shaft architecture. A heavier engine required the Lockheed TriStar to burn more fuel just to carry the power plants. To restore the promised fuel economy and thrust guarantees that Lockheed had legally locked into the contract, the Rolls-Royce engineers had to push the high-pressure core harder. They had to raise the internal operating temperatures, which required entirely new, highly complex cooling channels to be machined into the turbine blades so they would not melt. The RB211 was essentially being redesigned in real time on the factory floor, while the clock ticked down to Lockheed's delivery deadlines. The financial consequences were devastating. Under the fixed-price contract signed in 1968, Rolls-Royce could not pass these massive new research, development, and manufacturing costs onto Lockheed. Every pound spent redesigning the titanium fan, testing new containment rings, and remachining the hot section came directly out of the reserves in Derby. At the same time, the project was battered by the external pressures of Force 4, fuel, oil, austerity, supply chains, and energy shocks. As the 1970s dawned, Britain was gripped by severe economic inflation. The cost of raw materials, particularly the high-grade aerospace titanium being forged in Sheffield, was skyrocketing. Labor costs across the Midlands were rising as unions demanded higher wages to match the inflating cost of living. The original cost estimates that Rolls-Royce had presented to the British government and Lockheed were completely detached from the new reality. By the autumn of 1970, the accountants in Derby realized the terrifying scale of the disaster. Because of the fixed-price agreement and the soaring inflation, Rolls-Royce was losing millions of pounds in development. Even worse, calculations showed that once the assembly lines actually started full production, the company would lose hundreds of thousands of pounds on every single RB211 they shipped to California. The more engines they built, the faster they would bleed to death. In a desperate bid to survive, Rolls-Royce executives approached the British government for a massive emergency bailout. The state, horrified at the prospect of losing its premier engineering institution, initially agreed to inject tens of millions of pounds in additional launch aid, but it was like pouring water into a shattered vessel. The R&D burn rate at the Sinfin test site was consuming cash faster than the Treasury could print it. The engineers in the machine shops were finally beginning to solve the titanium weight problem, pushing the three-shaft design to work perfectly with the heavier metal. But the mechanical triumph was too late. The system around the engine had already collapsed, and the British winter was about to bring the final reckoning. By the bitter winter of January 1971, the crisis surrounding the RB211 could no longer be contained within the boardroom. Rolls-Royce was losing millions of pounds every week. The sheer scale of the engineering redesign, forcing the three-shaft architecture to compensate for the heavy titanium fan, had translated into a financial black hole. The British government, led by Prime Minister Edward Heath, commissioned an independent audit of the program. The resulting numbers were catastrophic. To finish the engine, certify it for passenger flight, and fulfill the Lockheed contract, the state would need to commit hundreds of millions of pounds in further subsidies with no guarantee of ever turning a profit. For a conservative government fundamentally opposed to state intervention, it was an ideological nightmare. Across the Atlantic, the panic was equally severe. Lockheed's chairman, Daniel Houghton, made desperate transatlantic flights to London, begging the British government to keep the Derby assembly lines moving. Lockheed had staked its entire corporate existence on the L-1011 TriStar, and the aircraft was designed exclusively around the physical dimensions of the RB211. There was no backup engine. If Rolls-Royce stopped building the power plant, Lockheed would almost certainly go bankrupt, pulling down a vast network of global aviation trade. In the Midlands, the human toll of the crisis was beginning to manifest. The town of Derby was effectively built around the engine company. For generations, securing an apprenticeship at Rolls-Royce meant a job for life, a promise of stability forged in aluminum and steel. Now the machinists cutting the complex turbine discs and the fitters assembling the high-pressure cores worked under a cloud of existential dread. The factories were still deafeningly loud. The foundries were still pouring metal, but everyone knew the money had run out. In a desperate final attempt to salvage the mechanical soul of the project, Rolls-Royce coaxed Sir Stanley Hooker, one of Britain's most legendary aero engineers, out of retirement. Hooker returned to Derby and immediately assembled a team of veteran engineers, many of them also retired, to ruthlessly attack the RB211's remaining flaws. They walked onto a factory floor that was gripped by financial paralysis and stripped away the hubris that had infected the early design phases. They stopped trying to build an impossible miracle and focused on making the heavy, titanium-bladed engine reliably function. They redesigned the combustion chambers. They painstakingly altered the aerodynamics of the compressor vanes to restore the lost efficiency. It was grueling, unglamorous work, altering metal tolerances by fractions of a millimeter. But engineering brilliance could not outrun the balance sheet. In London, the banking syndicates finally refused to extend any further credit. The original fixed-price contract had become a financial suicide pact. On the morning of 4th of February 1971, the Rolls-Royce Board of Directors accepted the inevitable. They officially called in the receiver. The company was bankrupt. When the news was broadcast, a physical shockwave hit the Derby factory gates. Men in oil-stained overalls who had spent their entire working lives building the engines that powered British civil and military aviation stood in stunned silence. The company that had built the Merlin, the name that had defined British mechanical superiority for more than half a century, was dead. The massive test stands at the Sinn Féin site felt like the monuments of a failed empire. Force 7, nationalisation, privatization, and brand survival, was about to rewrite the history of British engineering. The British government could not let the aerospace capability of the nation vanish overnight. In an unprecedented and deeply reluctant move, the state intervened. They nationalized the aero engine division, taking it entirely into public ownership to guarantee the survival of the RB211 and to prevent Lockheed's immediate collapse. The famous luxury car division and crew, which was still profitable and completely untainted by the jet engine disaster, was severed from the parent company and eventually privatized. The legendary Rolls-Royce name was cleaved in two, separated into entirely different corporate entities. The brand was saved, but the old, proud, independent company that had confidently challenged the American giants in 1968 was gone forever. In the midst of this corporate carnage, Hooker's engineering team finally achieved the impossible inside the heavily reinforced test cells. The redesigned, heavier RB211 began to hit its thrust targets. The three-shaft architecture, freed from the impossible constraints of the original budget, finally delivered the incredible thermodynamic efficiency it had promised years earlier. It was a mechanical triumph, built on top of a financial ruin. The engine finally worked. The massive fan turned. The titanium held together. The test cells roared. The thrust targets were met, but the money had vanished. The independent empire fell. The badge remained. The company behind it had changed forever. The company was nationalized. The old name was broken. But inside the hangars at Derby, the heavy, expensive, delayed engine was finally ready to fly. The L-1011 TriStar finally entered commercial passenger service in 1972. By the time the massive wide-body aircraft carried its first passengers into the sky, the world around its engines had irrevocably changed. The independent British company that had designed the power plants was dead, decisively split apart by the government. The luxury car division and crew had been spun off into a separate, private entity. The aero engine division in Derby was now a state-owned enterprise, rescued from absolute oblivion by the taxpayer. But up in the cold, thin air of the upper troposphere, the RB211 was doing exactly what its engineers had promised it would do. The heavy, delayed, brutally expensive engine was a mechanical triumph. The three-shaft architecture, the radical design that had forced the Midlands machinists to work to impossible, unforgiving tolerances, proved to be incredibly rigid and phenomenally reliable. As the TriStars flew their transatlantic routes, airlines quickly realized that the Rolls-Royce power plants were consuming significantly less fuel than their two-shaft American rivals, the Pratt& Whitney JT9D and the General Electric CF6. The RB211 was so good that its survival ultimately outlasted the aircraft it was originally built for. Lockheed, battered by the delays and fierce aerospace competition, eventually abandoned the commercial airliner market altogether, but the British engine lived on. By the late 1970s, Boeing realized the sheer potential of the Derby design and offered the RB211 as an option on the Boeing 747 jumbo jet. It fundamentally transformed the long-haul economics of the aircraft. British Airways, Cathay Pacific, and Qantas ordered vast fleets of 747s powered by the Derby engines, relying completely on a machine that had once been considered a catastrophic national failure. Today, the memory of that crisis survives in the hands of the people who built it. In Midlands pubs and local historical societies, retired machinists and fitters still talk about the bitter winter of 1971. In transport museums, aviation archives, and auto jumbles across the country, you can still find the thick, oil-stained service manuals for the early RB211 variants. These heavy binders, filled with exploded technical diagrams of the three concentric shafts, are physical artifacts of a time when human hands had to perfectly align metal to contain over 40,000 pounds of thrust. The British preservation community, the engineers and volunteers who maintain historic aviation displays at places like the RAF Museum or Duxford, know exactly what this power plant represents. This is where the story of the RB211 separates itself from mere industrial nostalgia. When we look back at the collapse of British motorcycle empires, the silent triumph twins outside old cafes, or the demise of British Leyland, we usually see a story of obsolete machinery being overtaken by a changing world. The RB211 is the exact opposite. The engine did not fail because it was obsolete. It failed because it was too far ahead of the financial and metallurgical reality of its time. Today, if you walk onto the factory floor at Derby, or look closely at the engines hanging beneath the wings of a modern Airbus A350 or Boeing 787, you will not see the RB211 name. You will see the Rolls-Royce Trent. But the Trent family, the engine family that dominates modern global aviation, is simply the direct evolutionary descendant of the RB211. The Trent engines still use the exact same three-shaft architecture that broke the original company. And in a final, profound twist of engineering irony, the modern Trent engines use hollow titanium blades and advanced composite materials. The black carbon fiber fan blades, the Hyfil dream that shattered under the bird strike test and triggered the bankruptcy, eventually became the global aerospace standard. The British engineers in 1968 were not wrong about the physics. They were just 30 years too early for the chemistry. In 1987, the Rolls-Royce Aero Engine division was successfully privatized, returning to the open market as a highly profitable, globally dominant corporation. It survived because the state stepped in, but it thrived because the foundational engineering of the RB211 was fundamentally correct. The legacy of the engine is a brutal lesson in the realities of Force One: iron, aluminum, fuel, and manufacturing costs. A machine can be mathematically perfect, mechanically brilliant, and entirely necessary for the future, yet still destroy the system that tries to build it under the wrong contract. The RB211 proved that the cost of an engineering revolution is sometimes higher than a single company can bear. Britain lost an independent corporate empire in February 1971, but in exchange it secured a permanent place in the modern wide-body age. The engine kept the foundries pouring, the machine shops cutting, and the Derby test cells roaring into the 21st century. It was the price of survival, forged in titanium and paid for in crisis. Somewhere in a British aviation museum, an early RB211 now sits silently on a steel display stand. The intricate concentric shafts are motionless. The heavy titanium fan blades gather a fine layer of dust under the gallery lights, holding on to the memory of a time when a single screaming turbine nearly broke a nation's pride, and then carried it into the future. See you in the next one.